Welcome back. This is a recap video for the Extremely Open Science Sardine stream we did on Tuesday, but I maybe want to go back a little bit before that and just do a recap of the project as a whole. So the goal of the project is to test this intuition that we have based on some observational data that we could, when we have metagenome assembled genomes, MAGs, that come from Oxford Nanopore data in particular, we have a different error pattern than the ones that come from Illumina, and in particular we start to have these small indels that cause interrupted genes, and this is something that's not being well picked up by existing quality control tools like CheckM or CheckM2, and so wanted to turn this intuition into an actual tool. But before that, what we've been playing around with is trying to see whether it's really true by using simulation. So we simulated genomes, or we simulated adding mutations into genomes with a fairly simplistic model, but we took E. coli, Bacillus subtilis, a couple of these other very well studied genomes, and we've been playing around with those. So I'm gonna now start sort of sharing my screen, and so this is the Sardine project, and we've computed a lot of these things already, and what we've been doing lately is looking at the computation outputs. And so here I'm gonna run a bunch of this already as I'm talking through it, so that as I'm talking through it. So we've been looking at these, in particular trying to understand whether we can take the outputs from CheckM2. So CheckM2 is this existing tool. What CheckM2 does is it predicts genes using Prodigal, and then uses Diamond to map those genes to KEGG orthologous groups, KOs, and then uses the set of KOs to infer whether this is a complete genome or a potentially contaminated genome. So ideally, would also from the point of view of the tool, it would be nice to be able to reuse the CheckM2 results. So say a user runs CheckM2, as they should already be doing, and then we can quickly run Sardine as a secondary check, reusing a lot of the computation that was done by CheckM2, so that and just giving the user a little bit more information on the quality of their genome, right? So as part of that, we've been trying to see whether, as we increase the number of mutations, or simulated mutations in this case, whether we do have more short genes, and we saw that we did. That's where we had left things off. Is that we had a lot of, we have more and more short genes as we increase the number of mutations, but it wasn't 100% clear how to transform that into because we were trying to find until this week, was trying to find if there's a way where we could say, okay, thresholding and cleaning up the data so that any remaining KOs that were quote unquote too short would be signed that something's wrong. But it didn't seem to be that easy. So this week decided to look at it a little bit in a different way, and in particular I'm just gonna run this and while this is running, I'll just a little bit talk you through it. So in particular, so we had already seen, and I'm gonna open so we had let me see here, for example, this one for Bacillus subtilis. So we had already seen plots like this one in previous weeks, where here wild type adding 100 mutations, adding 100,000 mutations, or 1,000 mutations, and so this is a cumulative distribution plot, and so 0 meaning that the KO is the size we expect it to be. We've also been exploring using different sources for this baseline, but settling on having the GMGC complete gene set as a potential set of baseline. So 0 means that this is roughly the same. So these are Z scores. This is roughly the same as we'd expect. And then -5 means we're 5 standard deviations below expectation. This means it's an extremely short gene for its KO. And what we've been looking at is that there is this gap here. So it's probably very difficult to distinguish 100 mutations from the baseline. So again, 100 mutations, this might be, some of them might not fall into protein coding gene. Some of them might fall towards the end of a protein coding gene or might not cause a frame shift. And so not all of these will actually cause a gene shortening. So there's only a handful of genes, that maybe low tens of genes that are, but 1,000 we already see this gap. And you can see that we don't see the gap on the other side. So it's much more likely that the mutation disrupts a gene and makes it shorter rather than it increasing the size of the gene, right? And so this week, looking at this, looking at this. Let's see, this is done now here, but we also always saw that even in the this is still computing, but even in the even in the high quality genomes, there are still a handful of genes, handful of KOs that were very short, much shorter, and particularly saw that last week that there's somewhere the E. coli variant seems to be the outlier, much shorter than everything else, but it's in this E. coli K12, which is probably as good as a genome can get. And so that might actually just be biological, and we do know that there are some true pseudogenes. So this week I thought, okay, instead of trying to clean up and get rid of, let's just see if we can find potentially an overabundance. And so ideally what we would like to do is to look at the area under the curve here, and have that as the, as our metric. But instead we're going to do something a little bit different, and let's see. And actually here the result is here, so I'm just going to show you the result. Is to take the z-scores below -4. So we're taking this. It's a bit of a parameter. We'll have to figure out exactly how to do it later. Probably it's not just the sum. Probably the area under the full area under the curve is a better approach. But just to test our intuition, it's very easy to implement the sum of this sum. This is what we did. So this is what we did here. We take z below -4, and then we just sum. Right? And we do this for all potential mutations. And so when we plot this as a number of mutations, and you can see, so E. coli, this value goes more and more negative. So you can see that E. coli actually starts more negative than the other ones, and then the others quickly go down. And here I've plotted in a dashed line the value at 0. So there's probably needs to be some calibration at some point to find exactly what's the minimum value at which you can still say, oh, this is potentially a bad genome, right? We don't want to distinguish. So, but I think this was a good advance this week. I think we can clearly see that in this range of 1,000 to 2,000 mutations, which is still very good. This is still, if a genome has in the millions of mutations, like about 4 or 5 million is a typical bacterial genome. Having 1,000, that's still a very low number, but we could already distinguish and pick it up. So I think this is still a reasonable, realistic number there, right? So a lot of progress there. I think potentially there's still this need to calibrate this to find out exactly what those parameters should be, exactly when should we say it's too low. Potentially tuning this to be, not just a sum, but to some area under the curve. So this idea I think has some potential. We will keep exploring it next week. Try to look at more genomes also as well. So in the meanwhile, I've put everything up on GitHub. Since this is still a very messy code, I've put it in the work in progress branch for now. But eventually it all get merged into a main branch, and eventually we'll get a slightly cleaner version of this. I think, as you saw in this recap, it takes a while to run it. Ideally, we would have to. So we'll do a little bit cleanup next week. We'll do a little bit more, figuring out, maybe adding a couple more genomes to the mix, and maybe start thinking about adding mags that come from real genomes to the mix as well. So we'll do that. So subscribe. You can also find things about it in the mailing list, on the Discord channel, or I'll see you next week.